Welcome back. Tonight we're going to explore rivers, those ancient ribbons of water that have been carving their way through landscapes since long before anything was alive to witness them. If you enjoyed this journey, consider subscribing so you can drift off to more stories like this one. Now let's begin. Rivers are bodies of flowing water that move continuously downhill, following gravity's patient pull toward the sea. It's such a simple thing, really. Water flows downhill. You've known this since you were small enough to watch rainwater running down a driveway, tracing its path with your finger. But there's something profound hidden in that simplicity. Rivers don't rush toward the ocean in straight lines. They meander and curve, they split and rejoin, they carve canyons and build deltas. All of it, every twist, every deposited grain of sand, every canyon wall is just gravity, working so slowly you'd never notice it in a lifetime, reshaping entire continents. Over millions of years, these patient movements create the landscapes we walk through. Mountains become plains, highlands become valleys, and all the while, the river just keeps flowing, one drop at a time, following the only direction it knows, down, always down. It's a kind of meditation if you think about it, this endless unhurried journey from high places to low ones, from mountain springs to the vast waiting sea. The Amazon River discharges more water than the next 7 largest rivers combined, releasing about 209,000 cubic meters per second into the Atlantic. Try to picture 209,000 cubic meters. It's almost impossible, isn't it? The human mind wasn't built for numbers like that. But here's another way to think about it. Every single second, the Amazon releases enough water to fill more than 83 Olympic swimming pools. Not per minute, not per hour, per second. And it does this continuously, forever, without pause, without rest. Right now, as you're lying here in the dark, the Amazon is pouring into the Atlantic. It was doing this before you were born. It'll be doing this long after you're gone. There's something almost comforting about that constancy, that eternal motion. While we sleep and wake, work and rest, age and change, the Amazon just keeps flowing at that same incomprehensible rate, mixing its fresh water with salt water in a boundary zone so vast you could sail through it for hours. The river is so powerful that it pushes fresh water hundreds of kilometers out to sea before the ocean can fully absorb it. These sailors have reported drawing fresh drinking water from the ocean, still tasting of the Amazon, while land was nowhere in sight. Rivers cover less than 0.0001% of Earth's surface, yet they contain about 0.006% of all fresh water on the planet. Such tiny numbers, such thin blue lines across the face of the Earth. If you looked at our planet from space, you might not even notice the rivers at first. They'd be almost invisible compared to the vast oceans, the sprawling continents, the swirling white clouds. And yet, despite their seeming insignificance, despite taking up barely any space at all, rivers are the arteries that keep entire ecosystems alive. They're the reasons civilizations grew where they did, the reasons cities stand where they stand. Human history has always bent itself around these narrow ribbons of flowing water. Because where rivers go, life can follow. We need them in a way that goes beyond mere utility. They've shaped how we think, how we organize ourselves, how we understand the landscape. It's remarkable, really, how something so small in proportion can be so essential. But perhaps that's the lesson here. Importance isn't about size, it's about connection, about movement, about being in the right place at the right time, continuously, reliably. Rivers are small, yes, but they're also everywhere they need to be. The word river comes from the Latin riparia, meaning riverbank, suggesting humans have always defined these waters by their edges. We didn't name rivers for the water itself. We named them for the boundaries they create, the edges where water meets earth. And maybe that tells us something about how we see the world. We understand things not just by what they are, but by what they touch, by the borders they create, by the line between this and that. A river is as much about its banks as it is about the water flowing between them. The bank is where the drama happens, where soil erodes, where trees lean over seeking water, where animals come to drink, where humans build their docks and bridges. The bank is the interface, the place where two worlds meet and negotiate their relationship. In Latin, riparia also gives us words like riparian, which describes the ecosystems that exist right at that edge. It's a whole category of life defined by proximity to the boundary. Not quite water, not quite land. Something in between. The river, in this sense, isn't just the flowing water, it's the entire system. The water and the boundary and the life that gathers there, all existing because of that edge between wet and dry. The Nile River flows northward for about 6,650 kilometers, making it one of the longest rivers on Earth. North. The Nile flows north. For ancient Egyptians encountering other rivers, this must have seemed like the natural order. Water flows toward the northern sea. But of course, rivers don't care about compass directions. They only care about down. It just so happens that for the Nile, down means north. Gravity doesn't consult maps. 6,650 kilometers. If you started walking at the Nile's source and walked its entire length, following every curve and bend, you'd be walking for months. You'd pass through rainforests and swamps, through deserts so harsh nothing grows, through ancient cities built on its banks thousands of years ago. You'd watch the river change character completely, from a narrow stream you could wade across to a massive, slow-moving giant, carrying the dissolved remnants of mountains and the fertility of an entire continent. And yet, despite its length, despite its grandeur, the Nile is just doing what all rivers do, following the slope of the land, moving water from high elevation to low elevation. The fact that this journey happens to be one of the longest on Earth, the fact that it flows backwards according to human expectations, doesn't make it any more or less remarkable to the water itself. It's just going where gravity pulls it. North happens to be down. Rivers can flow underground for miles, becoming invisible threads in the Earth's fabric. Imagine a river that simply vanishes. You're walking beside it, listening to the familiar sound of water over rocks, and then the riverbed opens up, and the water disappears into darkness. No dramatic waterfall, no obvious ending, just a gradual sinking into the earth, into limestone caves and hidden passages carved through stone over millennia. These underground rivers are real. They flow through complete darkness, carving chambers and tunnels that no light has ever touched, moving water through the secret architecture of the planet. They might travel for miles this way, completely hidden, completely unknowable unless you're willing to go down into the caves yourself. And even then, much of their passage is too narrow, too flooded, too dangerous for humans to follow. Sometimes these rivers resurface. They emerge from cave mouths or through springs, suddenly appearing as if by magic, flowing out into daylight from some mysterious underground source. The water might be cold, kept at a constant temperature by its journey through stone. It carries with it dissolved minerals, the taste of the rocks it's been touching in the dark. It's the same river, but transformed by its time underground, emerging into the world like a secret finally told. The concept of watershed, or drainage basin, means every raindrop that falls in a certain area will eventually flow into the same river system. Picture a raindrop landing on your roof. It rolls off, joins other drops, flows down the street into a storm drain, emerges in a creek, joins a stream, merges into a river, and eventually reaches the ocean. But here's the thing. Where that drop ultimately ends up was determined the moment it hit the ground. Its fate was sealed by geography. Every point on land belongs to a watershed, an area defined by the shape of the terrain, where all water flows toward a common outlet. If you're standing in the Mississippi watershed, every raindrop that falls around you will eventually make its way to the Mississippi River, step across the continental divide, and suddenly every drop flows toward a completely different ocean. It's as if the land itself is organized into invisible kingdoms, each paying tribute to a different river. The boundaries are real. They're written in the slopes and ridges of the earth, but they're invisible. You could walk across a watershed divide without noticing anything different. The grass is the same, the trees are the same. The air smells the same, but the water knows, gravity knows. On this side of the line everything flows east, on that side everything flows west. The land has chosen sides, and the rain has no choice but to obey. Rivers are remarkably young in geological terms. Most modern river systems are less than 10 million years old. 10 million years sounds ancient to us. It's a span of time so vast it's almost meaningless. Humans have existed for a tiny fraction of that. All of recorded history is a blink. And yet, in Earth's timeline, 10 million years is recent. It's young. Rivers, as permanent and eternal as they seem, are actually newcomers. The Earth is about 4.5 billion years old. The rivers we see today, the Amazon, the Nile, the Mississippi, they're all babies in that context. They're constantly being born, dying, and rerouting as the planet's surface shifts. Mountains rise and rivers change course. Ice ages come and go and rivers freeze or swell or dry up completely. Continental plates drift, and rivers that once flowed east might suddenly find themselves flowing west. This is happening now, just too slowly for us to perceive. Right now, the rivers you know are in the process of being born or dying or transforming into something else. In another 10 million years, most of them will be gone, replaced by entirely new systems we can't predict. The landscape will have changed so much that today's rivers would be unrecognizable. But there will be new rivers, following new paths, doing the same ancient work of moving water from high places to low places, just as they always have, just as they always will. The deepest river in the world is the Congo River, reaching depths of over 220 meters in some places, 220 meters deep. That's deeper than most lakes. That's deeper than many parts of the ocean near the shore. The Congo has carved underwater canyons in its riverbed. Not metaphorical canyons, but real ones, with walls and depths and darkness that never sees light. Imagine standing on a boat on the Congo's surface, looking down into water so deep that submarines would have room to maneuver. The pressure at the bottom would be crushing. The darkness would be absolute. And yet, this is a river, not an ocean. Fresh water, flowing downstream, happening to pass through a channel so deep it creates its own abyssal zone. We're only beginning to explore these depths. Special sonar equipment has revealed features we never knew existed. Rock formations carved by currents, sediment deposits laid down in layers, ecosystems adapted to the pressure and darkness. There are probably species down there we've never seen, living in what amounts to an underground river that happens to have an open top. The Congo River, like so many places on Earth, holds secrets in its depth that we're only just beginning to glimpse. A river's gradient, how steeply it descends, determines whether it flows gently or rushes violently over rocks. The same water, the exact same molecules of H2O. But depending on the angle of the ground beneath it, that water can be completely calm, glass smooth, barely moving, or it can be utterly chaotic, white with foam, roaring so loud you can't hear yourself think. The difference is just slope. Yeah, just the angle of descent. In flat terrain, rivers meander lazily, taking their time, often moving so slowly you could swim faster than the current. The water has time to deposit sediment, to build up sandbars, to create complex ecosystems in its slow motion. But put that same river on a steep mountainside and it transforms entirely. It becomes something wild, something powerful, something that can move boulders and carve stone. The water doesn't change, it's still just water following gravity. But the landscape changes everything about how that following happens, whether it's a gentle stroll or a frantic rush, whether it whispers or roars, whether it builds or destroys. It's all in the gradient, the slope, the angle of the earth beneath. Rivers create their own weather systems, generating fog and influencing rainfall patterns in their valleys. You've probably seen it, that low-lying mist that hangs over a river on a cool morning, refusing to lift until the sun gets high enough to burn it away. That's the river making its own weather. The water evaporates, meets cooler air, condenses into fog, and settles back down over the surface like a blanket. The river is breathing, in a sense, exhaling moisture that becomes visible in the right conditions. But it goes deeper than morning fog. Rivers actually influence rainfall patterns in their valleys. The moisture they release into the air can increase local humidity, making rain more likely. The temperature difference between the water and the surrounding land creates small air currents, gentle breezes that flow along the river valley. In some places, these river-generated weather patterns are reliable enough that local communities have learned to predict them, to expect certain conditions at certain times based on the river's behaviour. So rivers aren't just responding to climate, they're actively shaping it, at least in their immediate surroundings. They're participants in the water cycle, not just passive channels. Every river is a weather maker, a climate modifier, changing the air above it just by existing, just by flowing, just by being water exposed to air in a world where temperature and humidity are always in flux. The Amazon River was once thought to flow westward into the Pacific Ocean before the Andes Mountains rose and reversed its course. Imagine the Amazon flowing backwards, or rather, imagine that what we call backwards today was once forwards. Millions of years ago, before the Andes Mountains existed as we know them, the Amazon drainage system flowed in the opposite direction, westward toward what is now the Pacific Ocean. Then the Andes began to rise. Slowly, over millions of years, the Earth's crust buckled and lifted, creating a barrier where none had existed before. The river found its path blocked. Water pooled behind the rising mountains, forming vast inland seas. And eventually the water found a new way out, eastward, carving a new path toward the Atlantic. What's now the world's largest river is, in a geological sense, flowing backwards from its original course. The water doesn't know this, of course. It's just doing what water always does, finding the lowest path available. But we know we can read it in the rocks, in the sediment patterns, in the way the landscape is shaped. The Amazon has a history, a past life flowing in the opposite direction, and that former incarnation is still written in the earth if you know how to read it. Rivers contain less than 1% of Earth's fresh water, yet they're the primary source of water for most human civilizations. Less than 1%, it's almost nothing. The vast majority of Earth's fresh water is locked up in ice caps and glaciers. A good portion is underground in aquifers. Lakes hold some, but rivers are a tiny fraction of the total, and yet we've built our entire civilization around them. The reason is simple: rivers move. Unlike glaciers or underground water or lakes, rivers are going somewhere. They're reliable. They flow continuously. You can settle beside a river and know that the water will keep coming season after season, year after year. You can drink from it, irrigate from it, transport goods on it, use it to carry away waste. The river does work just by flowing. Every major city in history has been built on a river or near one. The Nile, the Tigris, the Euphrates, the Indus, the Yellow River, the Yangtze. These aren't just rivers. They're the foundations of civilizations. We organized ourselves around these flowing threads of water because they were the only reliable source we could count on. That less than 1% of Earth's fresh water has been responsible for nearly all of human development. We need them in a way that goes beyond mere statistics. The sediment carried by rivers created most of the world's farmland, depositing fertile soil in floodplains and deltas over millennia. Every grain harvest is, in a strange sense, ancient mountains dissolved and redistributed by patient water. The soil that grows our food was once rock, solid, hard, unchanging rock, somewhere upstream, maybe hundreds or thousands of kilometers away. Rain fell on that rock. Rivers flowed over it. Slowly, grain by grain, the rock was broken down, dissolved, carried away in suspension. The river carried that sediment downstream, and when it flooded, as rivers do, it spread that sediment across the floodplain. Layer upon layer, flood after flood, over thousands of years, the river built up soil, rich, dark, fertile soil, full of minerals that had once been trapped in stone. This is why river valleys are so productive. This is why the Nile Delta could feed ancient Egypt, why the Mesopotamian plains could support the first cities, why river floodplains everywhere become farmland. Now we're eating geology in a way. Every meal is connected to this process, mountains becoming soil through the endless work of flowing water. The bread on your table contains atoms that might have been part of a mountain peak millions of years ago, before a river decided to move them, molecule by molecule, to a field where wheat now grows. Some rivers, called ephemeral rivers, flow only occasionally, sometimes going years between flows. In deserts, there are rivers that aren't rivers most of the time. They're dry channels, sandy beds, empty ditches cutting across the landscape. They look dead, abandoned, but they're not dead. They're just waiting for rain that might not come for months or years or even decades. And then, when the rain finally comes, the river wakes up. Water suddenly appears, rushing through channels that were dust just hours before. The transformation can be shockingly fast, a dry wash becoming a raging torrent in minutes. Flash floods in deserts are real and dangerous because these sleeping rivers can wake up without warning, filled with water that fell miles away, arriving as a wall of churning brown liquid that sweeps away everything in its path. But most of the time, these ephemeral rivers are quiet, just empty beds, waiting. They're rivers in potential, rivers in memory. The channel is there, carved by past floods ready for the next one. They exist in a liminal state, not quite rivers, not quite dry land, but something in between. And perhaps that's appropriate for the desert, where everything exists on the edge between life and death, between water and dust. As the Mississippi River has changed course dramatically throughout history, sometimes shifting hundreds of miles from its previous path. The Mississippi isn't faithful to its channel. Over the centuries, it's wandered across the landscape like someone pacing in thought, trying different routes to the Gulf of Mexico. Cities that were once riverside ports now sit miles inland, stranded by a river that decided to flow somewhere else. There are places where you can see the old channels, curved depressions in the land, oxbow lakes that mark where the river used to turn, ghost rivers tracing paths that no longer carry water. The Mississippi left these signatures behind when it changed course, when it cut through a meander bend during a flood and found a shorter path, abandoning the old loop entirely. We try to control this wandering now. We've built levees and revetments trying to lock the Mississippi into its current course, but the river still wants to move. There's a constant battle between human engineering and the river's natural tendency to find new paths. Someday, maybe in a century, maybe in 10, the Mississippi might win that battle, might break through our constraints and carve a completely new route to the sea. It's happened before. It'll probably happen again. Rivers don't actually flow faster in the middle and slower at the edges. They flow fastest just below the surface in the centre. If you watch a river, you might assume the fastest water is right at the surface in the middle of the channel. But that's not quite right. The fastest flow is actually just below the surface, a few centimetres or metres down, depending on the river's depth. The very surface is slightly slower because of the friction between water and air. The edges are definitely slowest. That part is intuitive. Water dragging against the riverbed and banks creates friction that slows the flow, but the water's relationship with air is also friction, just less of it. So the sweet spot, the fastest flow, is in the middle depth-wise and middle width-wise, just beneath where air and water meet. This creates layers within the river, invisible zones of different speeds all flowing in the same direction but at different rates. It's part of why rivers are so good at sorting sediment. The different speeds at different depths create different carrying capacities. Heavy particles sink to the slow bottom layer and settle out. Light particles stay suspended in the faster upper layers and travel farther. Yet the river is stratified, organised into layers that we can't see but that determine how everything moves through it. A single river system can span multiple climate zones, experiencing tropical heat at its source and Arctic cold at its mouth, or vice versa. Some rivers are journeys through climate itself. They might begin in tropical rainforests, warm and humid, surrounded by dense vegetation and constant rain. As they flow, they might pass through savannas, then temperate forests, then eventually reach Arctic tundra near their mouth, where ice forms for half the year and the landscape is spare and cold. The same water that fell as warm rain in the tropics eventually flows past ice and snow. The same river that hosted tropical fish in its headwaters might have Arctic char near its mouth. It's a moving thread that connects completely different ecosystems, carrying not just water, but warmth or cold, nutrients from one climate zone to another, species that can only survive in certain sections. These long rivers are like climatic conveyor belts. They don't just exist in one environment, they pass through many. sampling different weathers, different seasons, different ecologies. A river that spans climate zones as many rivers in one, changing character completely along its length, but still connected, still the same water making the same journey from high elevation to low, from source to sea. The Yellow River in China is called China's Sorrow because its devastating floods have killed more people than any other natural feature in history. There's a dark side to rivers. We tend to romanticize them. Peaceful, life-giving, constant. But rivers can also be destroyers. The Yellow River has flooded so catastrophically, so many times throughout history, that it earned a name heavy with grief. China's Sorrow. Millions of people have died in its floods over the centuries. The same water that brings life through irrigation, that allows crops to grow and civilizations to flourish, can become catastrophically destructive when it escapes its bounds. The Yellow River carries enormous amounts of sediment, that's why it's yellow, and that sediment gradually raises the riverbed. Over time, the river actually flows higher than the surrounding land, held in place only by levees. When those levees break, the entire river can spill out across the floodplain with nowhere for the water to drain. It's a reminder that rivers aren't gentle. They're powerful geological forces that happen to be essential to human life. We need them, but we also have to respect what they can do when their power is unleashed. The water that gives life is the same water that can take it away, and the only difference is whether it's where we expect it to be or somewhere it shouldn't be. Rivers create natural borders between countries and states more than any other geographical feature. Look at a political map and notice how many borders follow rivers. The Rio Grande between the United States and Mexico, the Rhine through Europe, the Mekong through Southeast Asia, countless others. We use rivers to divide territory, to mark where one jurisdiction ends and another begins. It makes a certain kind of sense. Rivers are visible, permanent, more or less, and difficult to dispute. The border is wherever the water flows, but it also creates complications. Rivers move, they change course. A border that follows a river might shift over time as the river erodes one bank and deposits on the other. Land that was on one side of the border can end up on the other side without anyone moving it. The river just changed its mind about where to flow. There are legal frameworks for dealing with this, rules about whether borders move with the river or stay fixed in place. But fundamentally, we've chosen a dynamic living feature to mark our static political divisions. We've asked flowing water to hold still and define unchanging boundaries, and mostly it works, but there's always this tension between the river's nature to move, to change, to wander, and our need for it to stay put and mark a line that means something to humans, but nothing to the water. The phenomenon of river capture occurs when one river erodes backwards until it intercepts another, stealing its water. River capture sounds almost criminal, doesn't it? Like a heist happening in geological time, and in a sense that's exactly what it is. One river, eroding headward, cutting backward into the landscape, eventually breaks through into the drainage basin of another river. Suddenly, water that was flowing in one direction finds a new steeper path available. Gravity takes over, and the water changes allegiance. It abandons its old channel and flows into the capturing river instead. This leaves behind what's called a beheaded river, a stream that's lost its headwaters, and that now starts from a place that used to be somewhere in the middle of its course. The evidence is written in the landscape, a gap in a ridge where the capture happened, mismatched valleys that don't quite fit the streams flowing through them, elbows of capture where rivers make sharp, inexplicable turns. It's happening right now somewhere. Right now, there are rivers slowly eroding backwards, getting closer and closer to capturing their neighbours. The timescales are vast. These thefts take thousands or millions of years to complete, but they're real. Rivers compete for drainage area without knowing they're competing, and sometimes one wins by literally stealing the water that used to belong to another. Subglacial rivers flow beneath ice sheets, carving channels we can't see, lubricating glaciers and affecting how ice sheets move. Under the ice sheets of Greenland and Antarctica, there are rivers, complete rivers, flowing in total darkness beneath kilometers of ice, never seeing daylight, carving channels in bedrock that might not be exposed for millions of years. We only know they exist because of seismic studies, radar surveys, instruments that can peer through ice and detect the signature of flowing water below. These hidden rivers matter more than you might think. They lubricate the base of ice sheets, allowing glaciers to slide more easily toward the ocean. The water reduces friction between ice and bedrock, speeding up the flow of glaciers. In some places, subglacial rivers might be one of the factors determining how fast ice sheets can collapse, how quickly they can contribute to sea level rise. They're also among the least accessible environments on Earth, as to actually see one, you'd need to drill through kilometers of ice, then somehow explore a channel under crushing pressure in complete darkness, in water just above freezing. It's almost easier to imagine than to actually visit, and yet they're there, flowing right now beneath the ice, doing the same work all rivers do, moving water from high places to low places, just in one of the most extreme environments imaginable. The gradient of most rivers follows what's called a concave profile, being steeper near the source and gentler near the mouth. If you plotted a river's elevation from source to mouth, you wouldn't get a straight line. You'd get a curve, steep at first, then gradually flattening out as you approach the sea. This is the concave profile, and nearly every river follows it. It's not planned, not designed. It's just what happens when erosion and deposition reach a kind of equilibrium. Near the source, rivers are steep and fast. They have more erosive power, so they cut down into the bedrock more aggressively, but they also carry less water, so their ability to transport sediment is limited. As they flow downstream, they gather more water from tributaries, becoming larger and more powerful. But the slope decreases, so even though they're bigger, they flow more slowly. The increased volume and decreased slope balance out in a way that creates this characteristic curve. Rivers seem to solve an equation without knowing they're doing math. The concave profile is the answer to a problem posed by gravity, water volume, sediment load, and erosion resistance. Every river finds this solution independently, carving its way toward the same curve, and settling into this shape because it's the shape where forces balance, where the river can exist in something like equilibrium with the landscape it's flowing through. Some rivers maintain separate colours where tributaries meet, flowing side by side for miles before finally mixing. In Manaus, Brazil, the Rio Negro and the Amazon River meet. The Rio Negro is dark, almost black, stained with tannins from decaying vegetation. The Amazon is brown, thick with sediment from the Andes. When they meet, they don't immediately mix. Instead, they flow side by side for over 6 kilometers, a clear line visible between black water and brown water, two rivers occupying the same channel but refusing to blend. The reason is density and temperature. The waters have different properties, different temperatures, different speeds, yet different densities, and these differences keep them separate for a while. Eventually turbulence wins and the rivers do mix, but for those few kilometres you can see both rivers at once, flowing together but distinct, like a liquid border. It happens elsewhere too, wherever rivers with different characteristics meet. Clear water and silty water, warm water and cold water, fast water and slow water. The meeting of rivers is rarely instant. There's a transition zone, a place where both rivers exist simultaneously, side by side, before they become one. It's a reminder that mixing takes time, even for water, even when there's no barrier between them except their own different natures. River deltas are named after the Greek letter delta, because the Nile delta's triangular shape reminded Greek scholars of that letter. Thousands of years ago, Greek scholars looked at maps of the Nile delta and saw a triangle. The river split into multiple channels, spreading out as it approached the sea, and the overall shape resembled their letter delta, so they called it that. And now every branching river mouth in the world carries this bit of ancient alphabet geometry in its name. It's a small thing, but it shows how humans understand new landscapes by comparing them to what they already know. The Greeks didn't have a word for this particular landform, a place where a river spreads out and deposits sediment as it enters the sea. So they named it after a letter, and the name stuck. For thousands of years, across every language and culture that followed, we've called these features deltas. Not all river mouths form deltas, of course. Some rivers end in estuaries, mere drowned river valleys where the ocean has pushed inland. But where sediment accumulates faster than the ocean can remove it, where the river builds land faster than waves can erode it, a delta forms. A triangle of new land, built grain by grain, shaped like a letter from an ancient alphabet that gave it a name we still use today. The Ganges River supports more people than any other river system, providing water to about 400 million people. 400 million people. That's roughly 1 out of every 20 humans alive, all of them depending directly or indirectly on a single river system. The Ganges isn't just a river, it's a lifeline for a significant fraction of humanity. It provides drinking water, irrigation for crops, transportation, waste disposal, ritual purification. People are born beside it, live beside it, die beside it. The pressure on the river is immense. 400 million people need water every day. They need it for drinking, cooking, bathing, farming, industry. The Ganges provides all of this, but it's not infinite. Water withdrawn from the river might not return. Pollution builds up. During dry seasons, the flow decreases while demand remains constant. The river that has sustained civilizations for thousands of years is being asked to do more than it might be able to sustain, and yet it keeps flowing. Every day, the Ganges carries snowmelt from the Himalayas down through the plains, through cities and fields, through sacred gates where pilgrims bathe, through irrigation channels and treatment plants, eventually reaching the Bay of Bengal. 400 million lives connected to this single thread of flowing water, this ancient river that predates nations and will likely outlast them. Rivers can flow uphill in rare circumstances when tides or seismic events create temporary reversals in flow direction. It sounds impossible. Water flowing uphill, but it happens. Not often and not for long, but it's real. When ocean tides are strong enough, they can push back against a river's flow, creating a temporary reversal. The river appears to flow upstream, back toward its source, defying gravity for a few hours until the tide recedes and normal flow resumes. Seismic events can do it too. An earthquake or landslide can create a wave that travels upstream, pushing water backward. For minutes or hours, the river flows the wrong way, water moving uphill through sheer force before gravity reasserts itself, and the river remembers which direction it's supposed to flow. These reversals are brief, temporary, almost glitches in the usual order of things. But they remind us that rivers aren't simple. They're not just gravity in liquid form. They're influenced by tides, by seismic activity, by the complex interaction of forces that sometimes, in rare moments, can overpower the steady pull downward. For a little while, water can flow uphill, and then, inevitably, it remembers. Down. Always down, in the end. The sound of a flowing river creates pink noise, which has different frequency characteristics than white noise. Pink noise. It's a technical term from acoustics. White noise is equal energy at all frequencies, every pitch equally loud. A kind of audio chaos that sounds harsh, like static. Pink noise is different. It has more energy at lower frequencies, less at higher ones. It sounds more natural, more organic, more like the sound of a river. There's something about the particular acoustic signature of flowing water that human brains find soothing. It's not monotonous like white noise, but it's not melodic either. It's somewhere in between, complex enough to be interesting, simple enough to fade into the background. The combination of different water sounds, splashing, gurgling, rushing over rocks, creates this pink noise spectrum almost perfectly. Maybe that's why rivers have always drawn us. Maybe there's something in our evolutionary history that associates the sound of flowing water with safety, with the presence of a resource we need to survive. Or maybe it's simpler. Maybe our brains just like sounds that have pattern without being predictable, complexity without demanding attention. The river sounds the way it sounds, and we find that sound peaceful, and perhaps that's explanation enough. Braided rivers split into multiple channels that constantly merge and diverge, creating ever-changing patterns from above. From the air, braided rivers look almost abstract, geometric patterns of water and sediment, channels splitting and rejoining in complex webs that seem almost alive. And in a sense, they are alive. The pattern changes constantly. Channels that existed yesterday might be dry today. New channels open up, old ones fill with sediment. Islands appear and disappear. The river is plural, many streams occupying the same valley, never settling on a single path. Eager braided rivers form where there's abundant sediment and variable flow. The river deposits sediment in bars and islands, then splits around them. During high flow, some channels carry more water. During low flow, others dry up completely. The river's always rearranging itself, always solving the problem of how to move water and sediment through this valley most efficiently. If you stood beside a braided river and watched for years, you'd see the landscape constantly rewriting itself. The map would never be accurate for long. The river would redraw its own boundaries daily, creating a geography that exists only in that moment. It's a kind of impermanence made visible, the landscape refusing to settle, to fix itself, choosing instead to remain in constant flux. The world's shortest river is the Roe River in Montana, USA. By measuring just 61 meters from source to mouth, 61 meters, that's about 200 feet. You could walk the entire length of the Roe River in less than a minute, and you'd barely get your feet wet. It's hardly more than a stream connecting a spring to the Missouri River, a brief interlude between source and confluence. And yet it's officially recognized as a river, complete with a name and everything. There's something charming about this, isn't there? The idea that rivers can be this small, this brief, and still count. We tend to think of rivers as grand, the Amazon, the Nile, the Mississippi, but rivers exist at every scale. Some span continents, some span parking lots. They're all doing the same thing, moving water from high places to low places. Length doesn't matter, volume doesn't matter. If it flows, if it connects source to destination, it's a river. The Roe River is a reminder that geography comes in all sizes. Greatness isn't required. A river can be 6,650 kilometers long, or 61 meters long, and it's still a river, still following gravity's pull, still part of the endless cycle of water moving through landscapes on its way back to the sea. Rivers in limestone regions can disappear into sinkholes and flow through cave systems before re-emerging miles away. Limestone is soluble. Water, slightly acidic from dissolved carbon dioxide, can dissolve it over time. So in limestone regions, rivers don't just flow over the surface, they flow through it. A river will be flowing along normally, and then the ground opens up and the water pours into darkness, into a sinkhole that leads to underground passages carved through the stone. These are called losing streams or sinking streams. They trade the sky for darkness, becoming underground travellers for part of their journey. Down there in the caves, they carve chambers and tunnels, create underground waterfalls, flow through passages no light has ever reached. The water continues its journey, just invisibly, flowing beneath the surface while the riverbed above sits dry and empty. Sometimes these rivers resurface. They emerge from cave mouths or through springs, suddenly appearing as if by magic, flowing out into daylight from some mysterious source. The water is cold, kept at a constant temperature by its time underground. It tastes different, mineralized, carrying dissolved limestone. It's the same river that disappeared miles upstream, but transformed by its passage through the Earth's hidden architecture, emerging like a secret finally told. The temperature of river water varies surprisingly little throughout the year compared to the air above it. Air temperature might swing 40 or 50 degrees between summer and winter, but river temperatures change much more gradually. Water has what's called high thermal mass. It takes a lot of energy to heat it up or cool it down. So even when the air is freezing, the river might stay relatively warm. Even when the air is scorching, the river remains cool. This makes rivers stable havens when the atmosphere swings between extremes. Fish and other aquatic organisms don't have to deal with the wild temperature fluctuations that land animals face. The river buffers them, moderates the extremes, provides a more consistent environment. In summer, the river is a refuge from heat. In winter, it's a refuge from cold. There's something comforting about this stability. While everything else changes, the seasons turn, the air heats and cools, the landscape transforms from green to brown to white and back, the river maintains a more even temperature, changing slowly, resisting the chaos above it. It's another way rivers create their own environments, their own microclimates, their own rules that don't quite match the world around them. Tidal rivers flow backward twice daily where they meet the ocean, creating zones where the direction changes with the moon. Near the coast, rivers become undecided. They pulse in and out with the tides, flowing toward the ocean when the tide is low, flowing back upstream when the tide is high. Twice a day the river changes its mind about which direction it's flowing. Gravity pulls it toward the sea, but the moon's gravity, acting through the ocean's tides, can temporarily overpower that pull. In these tidal zones, the river isn't quite a river and isn't quite part of the ocean. It's something in between, brackish water, a mix of fresh and salt, flowing one way and then the other, never settling, never deciding. The organisms that live here have to adapt to constantly changing conditions. Salinity that varies with the tide, current that reverses twice daily, water levels that rise and fall on the moon's schedule. It's strange to watch a river flow backward. It feels wrong, like seeing time run in reverse. But it's natural, just a consequence of two forces, gravity and tides, competing for control. Most of the time, gravity wins. But near the ocean, twice a day, the tides win instead, and the river briefly forgets which way it's supposed to flow. The Amazon River has no bridges crossing its main channel, despite being one of the most famous rivers on Earth. The Amazon is one of the most recognized rivers in the world, flowing through one of the most populated countries in South America, and yet no bridge spans its main channel. Not one. There are bridges over tributaries, over smaller channels, but the main Amazon remains unbridged. The reasons are practical. The river is enormous, in some places over 10 kilometers wide. It floods dramatically, rising 10 meters or more during the wet season. The banks shift, the channels migrate, the whole river system is in constant motion. Building a bridge that could handle these conditions would be an engineering challenge of extraordinary magnitude. The costs would be staggering, and the communities on either side are separated by such distances that ferry service has been sufficient. So the Amazon remains unspanned, one of the last great rivers without a bridge, flowing from the Andes to the Atlantic with nothing crossing it but boats and wildlife. There's something fitting about that. The largest river in the world remaining unbound by human infrastructure, too vast and too dynamic to pin down with concrete and steel. Fact 35. Rivers create microclimates along their banks, moderating temperatures and increasing humidity in otherwise dry landscapes. Walk toward a river in the desert and you can feel the climate change with each step closer. The air becomes cooler, more humid. Plants appear that couldn't survive 50 meters away. The temperature drops noticeably near the water. The river creates its own weather, its own little bubble of moisture and moderated temperature in an otherwise harsh landscape. This is the riparian zone, the area immediately adjacent to the river, and it's a completely different world from the surrounding terrain. The river provides water, obviously, but it also provides evaporative cooling. Water evaporating from the surface pulls heat from the air. The vegetation that grows near the river releases more moisture through transpiration. The result is a corridor of different climate threading through the larger landscape. These microclimates matter enormously to the life that depends on them. In arid regions, the riparian zone might be the only place where certain species can survive. Trees that need consistent moisture can grow beside the river even when the surrounding land is too dry to support them. The river becomes a lifeline not just through its water, but through the climate it creates around itself. The fastest river rapids can exceed 40 kilometers per hour, creating turbulent forces capable of moving boulders. 40 kilometers per hour doesn't sound that fast. You could drive faster on a residential street, but imagine that speed translated to millions of liters of water crashing through a constricted channel filled with rocks. The kinetic energy is immense. The turbulent forces, water hitting obstacles, swirling in eddies, accelerating through narrow gaps, can move boulders weighing tons. In these rapids, Water becomes sculptor and destroyer simultaneously. It picks up rocks from the riverbed and hurls them downstream. Those rocks, tumbling and grinding against each other and against bedrock, carve the channel deeper. The river is reshaping itself through pure kinetic persistence, wearing away stone through the accumulated impact of billions of water molecules moving at high speed. Stand beside rapids like these, and you feel the power viscerally. The ground shakes. The air is full of spray. The roar drowns out all other sound. It's a reminder that water, despite seeming soft and yielding, can be one of the most powerful forces on Earth when it's moving fast enough and concentrated enough. These rapids are water at its most violent, its most transformative, doing in hours what gentle flow might take centuries to accomplish. Some rivers contain natural oil seeps, flowing with hydrocarbons mixed into their water, creating rainbow sheens millennia before human pollution. Not all oil in rivers is pollution. In some places, the earth itself leaks oil into waterways through natural seeps. Underground petroleum deposits find their way to the surface through cracks and fissures, emerging into rivers and creating rainbow sheens on the water's surface that have nothing to do with human activity. These natural oil seeps have existed for millions of years, long before humans were around to pump oil out of the ground. Ancient peoples knew about them. Some rivers were even named for the oil they carried. The La Brea tar pits in Los Angeles are fed by natural seeps that have been active for tens of thousands of years. It's a reminder that the earth itself sometimes makes rivers that would fail modern purity tests. Nature isn't always clean by our standards. Rivers can naturally carry hydrocarbons, heavy metals, ESO radioactive elements, things we consider contaminants but that are just part of the geology in certain regions. The river doesn't care, it just carries what the landscape gives it, dissolving and transporting whatever it encounters on its journey to the sea. River meanders follow mathematical patterns described by sine curves, creating predictable shapes despite appearing random. A meandering river looks almost whimsical, doesn't it? Graceful curves that seem to follow no particular pattern, just wandering across the landscape. But if you measure those curves carefully, if you plot them mathematically, they follow sine curves, smooth, predictable oscillations that can be described with relatively simple equations. The river is solving a physics problem. It's finding the most efficient way to dissipate energy as it flows across a low gradient plane. The curves aren't random. They're the solution to equations the river solves unconsciously through erosion. Water flowing faster on the outside of bends erodes the outer bank. Water flowing slower on the inside of bends deposits sediment on the inner bank. This process naturally creates curves that follow sine wave patterns. So beneath the apparent randomness, there's order. The river's path can be predicted, at least statistically, because it's following mathematical rules embedded in the physics of flowing water. Different rivers in different places will create similar patterns because they are all solving the same equation, all finding the same kind of solution through the same physical processes. The sediment load of rivers can be so heavy that the water becomes denser than normal, flowing along the ocean floor when it reaches the sea. When a river carrying enormous amounts of sediment enters the ocean, something strange can happen. The sediment-laden water is denser than seawater. Instead of mixing and dispersing at the surface, it sinks. It flows along the ocean floor as an underwater river, a current of turbid water carrying mountain debris into the deep sea. These underwater rivers create what are called turbidity currents. They can flow for hundreds of kilometers across the ocean floor, carving submarine canyons, depositing sediment in deep-sea fans, transporting material from the continental shelf to the abyssal plains. They're powerful enough to snap underwater cables, fast enough to be dangerous to anything in their path. So the river doesn't really end at the coast. It continues invisibly beneath the ocean surface, still doing the same work it was doing on land, moving sediment from high places to low places. Just now the high place is the continental shelf and the low place is the deep ocean. The river has transformed into something invisible but still present, still flowing, still carrying its load of dissolved mountains toward a final resting place in the abyss. Ancient rivers are preserved in the geological record as paleo-channels, ghost rivers visible in sediment layers. By reading rocks, we can map rivers that flowed millions of years before humans existed to name them. The sediments they deposited, the channels they carved, the patterns they left behind, all of this is preserved in the geological record. These are called paleo-channels, ghost rivers that no longer flow but that still exist as patterns in stone. Sometimes these ancient river channels are important for practical reasons. They might contain groundwater, trapped in the porous sediments the river deposited millions of years ago. They might contain mineral deposits concentrated by the ancient flowing water. We can drill into them, extract resources from them, even though the river itself hasn't flowed for longer than humans have existed. It's a kind of immortality, in a way. The river is long gone, evaporated or diverted or dried up as climates changed and continents drifted. But its signature remains, written in the rocks, readable to anyone who knows how to interpret sediment layers and channel geometries. The river is dead, but not gone. It exists as memory, as pattern, as evidence of water that flowed through a landscape that no longer exists in a world we can only imagine. The Okavango River in Africa never reaches the ocean, instead spreading into a massive inland delta where all its water evaporates. Most rivers have a destination. They flow from source to sea, completing a journey that ends when fresh water meets salt water. But the Okavango River has no such ending. It flows into the Kalahari Desert in Botswana, spreads out into an enormous inland delta, and then simply disappears, evaporates, returns to the sky. The Okavango Delta is one of the world's largest inland deltas, covering thousands of square kilometers during the flood season. The water spreads across the landscape, creating temporary wetlands, feeding vegetation, supporting wildlife. And then, slowly, it evaporates under the African sun. Some seeps into the ground, some is taken up by plants, but none of it reaches the ocean. The river has no mouth, no confluence, no final destination. It just dissolves into air and sand. It's one of Earth's most unusual hydrological systems, a river with no ending, no completion of the usual cycle. The water still returns to the atmosphere eventually, still rejoins the global water cycle, but it does so directly, skipping the ocean entirely. The Okavango is a river that forgets to finish its journey, that stops partway through and decides to become sky instead. Rivers transport about 15 billion tons of sediment to the oceans every year, continuously rebuilding coastlines and deltas. 15 billion tons every year. That's the combined weight of all the sediment carried by all the rivers in the world to the oceans. Its mountains dissolved and redistributed, its continents slowly eroding grain by grain, making their way to the sea. This sediment doesn't just disappear into the ocean, it builds things. It creates deltas, extending coastlines out into the sea. It replenishes beaches, replacing sand that waves carry away. It creates new land where none existed before. The Mississippi Delta, the Nile Delta, the Ganges Delta, all of these are built from sediment carried by rivers, deposited layer upon layer over thousands of years. Rivers are conveyor belts moving mountains to the sea, never stopping, never resting. Right now, as you're listening to this, millions of tons of sediment are being carried downstream in rivers all over the world. Particles that were once part of mountain peaks are tumbling along riverbeds, making their way toward the ocean where they'll settle and become part of a delta, part of a beach, part of the ocean floor. The landscape is constantly redistributing itself through these flowing channels of water. The concept of river continuum describes how rivers gradually change from source to mouth in predictable ways. A river is not one thing but a progression, transforming its character along every meter of its length. Near the source, rivers are cold, clear, fast-flowing and narrow. They're dominated by physical processes, erosion, sediment transport. The organisms that live there are adapted to cold water and high currents. As the river flows downstream, it changes. It gets wider, slower, warmer. More nutrients enter from the surrounding landscape. The biological community shifts from organisms that can handle fast, cold water to those that thrive in slow, warm water. The river transitions from a place dominated by physics to a place dominated by biology. This progression is predictable enough that ecologists call it the river continuum concept. It's a framework for understanding how rivers work as systems, how they change continuously from headwaters to mouth. The river isn't segmented into discrete zones. It's a gradient, a smooth transition where every point is slightly different from the point just upstream and the point just downstream. The river is always becoming something else, never quite settling into a single identity. Some rivers reverse flow seasonally, including parts of the Tonle Sap River in Cambodia, which changes direction based on monsoons. The Tonle Sap River has two identities each year. For half the year it flows normally, draining Tonle Sap Lake into the Mekong River. Water moves from the lake to the river, following the usual downhill pattern. But when the monsoons arrive and the Mekong swells with floodwater, something remarkable happens. The Mekong becomes so full that it actually flows backward up the Tonle Sap River, filling the lake instead of draining it. The lake can triple in size during this reversal, transforming from a relatively small lake into one of the largest freshwater bodies in Southeast Asia. Fish populations explode. Fishing communities that were kilometers from the shore suddenly find themselves waterfront. And then, when the monsoons end and the Mekong's flood recedes, the river reverses again. It flows back out of the lake, returning to its normal direction. The river has two modes, two completely different flow patterns it switches between with the seasons. For months, it flows confidently in one direction. Then, as if changing its mind, it turns around and flows the opposite way for the other half of the year. The people who live along it have learned to expect this, to plan their lives around a river that can't decide which way it's going. River ice creates unique formations called ice jams that can cause catastrophic flooding when they break. In cold climates, rivers freeze, but they don't freeze evenly, don't freeze all at once. Ice forms on the surface, breaks apart, refreezes, piles up in chaotic jumbles. These ice jams are exactly what they sound like, traffic jams made of ice, places where broken ice chunks accumulate and create a blockage. Behind the ice jam, water backs up. It can't flow past the blockage, so it rises, flooding areas that are normally dry. And then, when the weather warms or the pressure becomes too great, the ice jam breaks. All that backed up water is suddenly released at once, surging downstream as a flood of water and ice chunks, sometimes piled higher than houses. Ice jam flooding can be more destructive than regular flooding, because it's unpredictable and violent. The ice itself becomes a battering ram, smashing into anything in its path. Frozen rivers become dams made of chaos, holding back enormous volumes of water until the inevitable thaw unleashes it all in a sudden, devastating release. It's water in its most chaotic, solid form, creating temporary barriers that eventually always give way. The Amazon River's mouth is so wide that the island of Marajó sitting in it is larger than Switzerland. The Amazon doesn't so much meet the ocean as it becomes indistinguishable from it across hundreds of kilometers. The mouth is so wide that standing on one side you couldn't see the other, and in the middle of this vast mouth sits Marajó, an island larger than entire countries, created by sediment the river deposited over millennia. Marajó's a world unto itself, home to hundreds of thousands of people, covered in rainforest and savanna, large enough to have its own ecosystems and regional variations. And it exists entirely because the Amazon brought sediment from the Andes and deposited it here, grain by grain, building land in the middle of its own mouth. Some rivers end with a simple confluence, a clear point where river water meets ocean water. The Amazon doesn't have that. It has a transition zone spanning hundreds of kilometers, a gradual blending that includes entire islands built from its own sediment. The river is so large that its ending is itself a geographic feature, a region defined by the meeting of fresh water and salt water on a continental scale. Rivers create riffle pool sequences, shallow, fast water followed by deep, slow water that repeat at predictable intervals. Even in their seeming randomness, rivers organize themselves into rhythmic patterns. Riffles, shallow sections where water flows fast over rocks, alternate with pools, deeper sections where water slows and collects. This pattern repeats predictably, like musical measures. It is spacing itself along the river at intervals that depend on the river's width and gradient. The spacing isn't arbitrary. It emerges from the interaction between flowing water and the riverbed. Water flowing over a riffle scours a pool downstream. Sediment deposited at the tail of the pool creates the next riffle. The pattern reinforces itself, becomes stable, creates a rhythm that you can predict once you understand the river's basic dimensions. Fish know these patterns instinctively. Riffles provide oxygen and food. Pools provide shelter and resting places. The alternating pattern creates habitat diversity, supporting different species in different sections. The river's rhythm becomes the rhythm of life within it, organizing biological communities according to the same physical principles that organize the water's flow. The Catatumbo River in Venezuela creates the world's most persistent lightning storms, where it meets Lake Maracaibo. There's a place where a river meets a lake and the sky lights up. The Catatumbo River flows into Lake Maracaibo in Venezuela, and at this confluence lightning strikes almost constantly. Not just during occasional storms, this happens up to 260 nights per year for up to 10 hours at a time. The phenomenon is so reliable it has a name, the Catatumbo Lightning. Scientists believe it's caused by a unique combination of factors: winds from the Andes meeting warm air from the lake, methane from decomposing organic matter in the wetlands, the specific topography of the region. Whatever the exact mechanism, something about this particular meeting of river and lake creates conditions that generate lightning more consistently than anywhere else on Earth. The lightning is silent, too far away to hear thunder, so it's just light, flickering in the sky, illuminating clouds from within, creating what must have seemed like magic to people who lived here before we understood atmospheric electricity. Even now, understanding it, it still feels magical. A river that makes lightning, that turns the sky into an electrical display night after night, year after year, for reasons we're only beginning to fully comprehend. Submarine rivers flow along the ocean floor in channels carved by sediment-laden water, denser than seawater. There are rivers under the ocean. Not metaphorical rivers, not ocean currents in the usual sense, but actual rivers, channels of denser water flowing along the ocean floor, carrying sediment, following defined paths, behaving like rivers even though they're underwater and composed of seawater mixed with sediment rather than fresh water. These submarine rivers can be enormous. The Black Sea has an underwater river flowing through it that's one of the largest on Earth if measured by water volume. It flows through a canyon on the seafloor, with banks and a channel just like a surface river, except it's hundreds of meters below the ocean's surface, invisible from above. They form when dense, sediment-laden water from river mouths sinks and flows along the ocean floor, or when dense, salty water from one ocean basin flows into another. The result is rivers within the ocean, invisible currents carrying continental debris to the abyss, sequel, carving channels we're only beginning to explore, doing underwater the same work that surface rivers do on land. The point where a tributary joins a larger river is called a confluence, from Latin meaning to flow together. Confluences are rivers' social moments where separate journeys merge into collective motion. Each tributary has its own story, its own source, its own watershed, its own character. And at the confluence, these separate stories combine. Two rivers become one. The water that fell as rain in completely different places, that travel different paths through different landscapes, suddenly joins together and continues as a single flow. Sometimes the meeting is obvious. Two different colours of water flowing side by side before mixing. Sometimes it's subtle, a barely noticeable increase in volume, but always, it's a transformation. Downstream of a confluence, the river is different. Larger, yes, but also carrying the combined character of both streams, a mixture of different watersheds and different histories. If you follow a river upstream, confluences are where it branches, where you have to choose which path to follow. Each choice takes you to a different source, a different story. The river is not a single line but a network, a tree of connections, and the confluences are the nodes where branches join, where separate becomes collective, where many become one. Rivers actively migrate across their floodplains, sometimes moving sideways faster than they move downstream. Over centuries, a river can walk across an entire valley while barely advancing toward the sea. This isn't a metaphor, it's literal movement. The river erodes one bank while depositing sediment on the other, shifting its channel sideways across the floodplain. The process is slow from a human perspective, but fast in geological terms. A river might move hundreds of meters sideways in a single human lifetime. This lateral migration creates the wide, flat valleys we call floodplains. The river has wandered back and forth across the valley floor, visiting every part of it over thousands of years. Farmland that sits beside a river today might have been the riverbed itself a century ago. Land on the far side of the valley might become riverbed a century from now. If you could watch this migration in time-lapse, the river would look almost alive, slithering back and forth across the valley like a snake, never settling, always moving. The channel we see today is just a snapshot, a single frame in a much longer movie of continuous lateral motion. The river is not a fixed feature carved into the landscape. It's a wanderer, exploring the valley it created, never quite satisfied with any particular path. The biological diversity in rivers rivals that of rainforests, with some river systems containing thousands of unique species. Rivers are biodiversity highways, creating corridors of life through otherwise inhospitable terrain. The Amazon River system alone hosts over 3,000 species of fish, more than the entire Atlantic Ocean. Some rivers contain species found nowhere else on Earth, adapted to specific conditions in specific stretches of water. The diversity isn't just about fish. There are freshwater dolphins, giant otters, countless invertebrates, plants adapted to periodic flooding, birds that depend on river ecosystems. Each part of the river, from rushing headwaters to slow lowland reaches, supports different communities of life, creating a gradient of biodiversity along the river's length. And much of this diversity remains unknown. New species are discovered in rivers regularly, especially in remote or poorly studied systems. There are probably fish swimming in Amazonian tributaries that science has never documented, invertebrates living under rocks that no one has ever identified. Rivers are among the most biodiverse ecosystems on Earth, and we're still learning just how much life they contain. Rivers can create natural bridges through a process called natural bridge formation, where the river cuts through rock leaving an arch. Sometimes a river curves so tightly that it almost touches itself, a meander that's nearly closed into a loop. Water flowing through the narrow neck of land between the two parts of the curve can erode through, creating a shortcut. The river abandons the long loop and flows through the new, shorter channel instead. What's left behind is an arch of rock, a natural bridge spanning what used to be the riverbed. The water that carved the passage eventually abandoned it, leaving stone sculptures as evidence of its former path. These natural bridges can be massive, spanning dozens of meters, strong enough to support vegetation, even trees, growing on top of them. They're temporary features in geological time. Eventually the arch will collapse, weathered by wind and rain, and the slow work of erosion. But for now, for centuries or millennia, they stand as monuments to the river's former course, bridges built by water and abandoned when the builder moved on to carve new channels elsewhere. The Nile River's annual flood was so regular that ancient Egyptians based their calendar on it. A river became time itself, measuring the year not in stars but in water rising and falling. Every year the Nile would flood, inundating the floodplain with water and nutrient-rich sediment. The flood was predictable enough that you could set your calendar by it. So predictable that ancient Egyptians did exactly that. Their year was divided into 3 seasons based on the Nile's behaviour. Akhet, the inundation season when the river flooded. Pere, the growing season when the waters receded and crops were planted. And Shimu, the harvest season when the fields dried out. The river dictated not just agriculture but the entire rhythm of life, the structure of time itself. The flood doesn't come anymore, not like it used to. The Aswan Dam controls the Nile's flow now, keeping it relatively constant year-round. The ancient calendar based on flooding is obsolete, replaced by modern measurements and modern agriculture. But for thousands of years, the river was the clock, the calendar, the measure of time passing in a civilization that organized itself entirely around the rhythm of rising and falling water. Some rivers maintain their courses across mountain ranges because they were already flowing when the mountains began rising. These are called antecedent rivers, and they're doing something that seems impossible, cutting through mountain ranges that should, by all logic, divert them. But the river was there first. It was flowing across a landscape before the mountains existed, and as the mountains rose, the river kept cutting downward at the same rate the land rose upward. The result is a river that flows through a mountain range in a deep gorge, maintaining a path that predates the mountains themselves. The river is older than the mountains, and its course preserves a memory of what the landscape looked like before the uplift began. These gorges can be thousands of meters deep, carved over millions of years by a river that refused to be diverted. It's a kind of geological stubbornness. The river could have been pushed aside, forced to find a new path around the rising mountains, but it kept cutting downward, maintained its course through sheer erosive persistence, and carving a channel through rock that was rising beneath it. The path is millions of years old, older than the mountains themselves, preserved by constant motion, by water that never stopped flowing. River water has an average residence time of about 16 days, meaning water molecules typically spend just over 2 weeks in rivers. Rivers are brief passages, not destinations, in water's endless cycle through Earth's systems. A water molecule enters a river, from rain, from groundwater, from a tributary, and spends about 16 days there before exiting, either into the ocean or by evaporating back into the atmosphere. 16 days. That's how long the river phase lasts on average, for any given molecule of water. It's a short visit in the grand scheme of water's journey. That same molecule might spend years in a glacier, decades in an aquifer, yes, centuries in the deep ocean. But in a river, just over 2 weeks. This rapid turnover means rivers are constantly being replaced by new water. The river you see today contains almost entirely different water molecules than the river you saw a month ago. The flow is continuous, but the substance is always changing, always being replaced. The river is permanent, but the water in it is temporary, just passing through on a journey that began somewhere upstream and will end somewhere downstream, before continuing on to the next phase of an endless cycle. The patterns rivers create when viewed from above, dendritic, trellis, radial, reflect the underlying geology with surprising precision. Rivers are map makers, tracing invisible structures beneath the surface through their branching patterns. Look at a river network from above, and you're seeing a kind of X-ray of the underlying geology. The pattern tells you what's beneath the soil. Dendritic patterns, branching like tree roots, form on uniform rock, where the river can erode equally in all directions. Trellis patterns, parallel tributaries joining a main stem at right angles, form where alternating hard and soft rock layers create linear valleys. Radial patterns, rivers flowing outward from a central point, form on volcanic cones or domes where water flows down all sides from a high point. The river doesn't know it's revealing anything. It's just following the path of least resistance, flowing where erosion is easiest, where rock is weakest, where valleys have already formed. But in doing so, it creates a map of the underground, a surface expression of hidden structures. The pattern is the message written in flowing water, readable from space. Glacial rivers fed by melting ice can increase their flow by 1,000% between night and day during summer. These rivers have daily personalities, transforming from streams to torrents with the sun's warmth. At night, when temperatures drop, glacial melt slows. The river becomes a trickle, sometimes shallow enough to wade across. But as the sun rises and temperatures increase, the glacier accelerates its melting. More water enters the river. By afternoon, that same river can be a raging torrent, 10 times its nighttime flow, too deep and fast to cross safely. This daily cycle creates a rhythm that everything in the ecosystem has adapted to. Fish move to different parts of the channel depending on flow, as plants grow only in zones that remain above water even during peak flow. Anyone travelling in glaciated mountains learns to cross glacial rivers in the early morning, before the day's melt has swelled them into barriers. It's a reminder that not all rivers are constant. Some pulse with daily rhythms tied to temperature and sunlight, expanding and contracting like breathing, transforming entirely between dawn and dusk. The river you crossed in the morning might be uncrossable by afternoon, and then crossable again the next morning, in an endless cycle driven by the sun's heat working on distant ice. The world's rivers contain about 2,120 cubic kilometers of water at any given moment, constantly being replaced by new water. 2,120 cubic kilometers. It's hard to visualize that much water. But here's what matters. It's constantly being replaced. Every drop is temporary, part of an eternal procession from mountain to sea and back again. The rivers contain this much water at any given moment, but the specific molecules change completely every few weeks. Think about what that means. The river is permanent, but the water in it is temporary. The channel, the banks, the name, those persist. But the actual substance, the H2O molecules, are just passing through. They arrived recently as rain or snowmelt. They'll leave soon as ocean water or atmospheric vapor. The river is less a thing and more a process, a continuous flow where nothing stays but everything continues. This is true of everything in a sense. We're all processes more than things, patterns that persist even as the components change. But rivers make it visible. You can see the water flowing past, can understand intuitively that it's different water from moment to moment, even though it's the same river. The river teaches impermanence just by existing, just by flowing. Some desert rivers flow entirely underground along their lower reaches, becoming invisible before reaching any destination. These rivers slip beneath the sand and simply fade away, neither reaching the ocean nor evaporating, just disappearing underground and never coming back up. They infiltrate into the ground, recharging aquifers, becoming groundwater instead of surface water. The channel remains dry and empty, marking where the river used to flow, where it might flow again if enough rain falls. In the driest deserts, this underground flow might be the only water in the region, and surface rivers are too exposed. They'd evaporate before travelling far. But underground, protected from the sun and wind, water can travel significant distances. The river hasn't stopped flowing, it's just become invisible, moving through sand and gravel beneath the surface. Sometimes you can detect these invisible rivers by the vegetation above them. Trees and shrubs with deep roots tap into the underground flow, creating green lines across otherwise barren landscapes. The plants mark the river's path even when the river itself can't be seen. The water is there, flowing in darkness beneath the surface, sustaining life from below while remaining hidden from view. The suspended sediment in rivers scatters light, which is why turbid rivers appear brown or grey rather than water's natural blue. Pure water, when you see enough of it, is blue. Not because it reflects the sky, but because water molecules preferentially absorb red wavelengths and scatter blue ones. But you rarely see this blue in rivers. Most rivers are brown or grey or sometimes green, depending on what they're carrying. The colour is a visual record of what the river is destroying and where it's been. Brown water means sediment, clay, silt, sand suspended in the flow. The particles scatter all wavelengths of light more or less equally, creating brown or tan tones. Green might mean algae or dissolved organic matter. Grey could mean glacial flour. Rock ground so fine by glaciers that it stays suspended almost indefinitely. So a river's colour tells a story. Clear water means low erosion, stable banks, resistant bedrock. Brown water means active erosion somewhere upstream. Mountains being worn down, these soils being carried away. The river is literally the colour of the landscape it's destroying, carrying evidence of its work suspended in every litre of flow. Rivers create nick points, sudden drops in elevation that migrate slowly upstream over thousands of years. A nick point is a scar in the landscape, a place where the river's gradient suddenly steepens, where there's a waterfall or rapid that seems out of place. These form when something changes, sea level drops, the land uplifts, a resistant rock layer is exposed. Suddenly there's a break in the river's smooth profile, a step it has to flow down, and then the nick point begins migrating. Water flowing over the step erodes the rock at its base, causing the step to move slowly upstream. It's like the scar is healing backward, the discontinuity moving against the flow, eroding away its own evidence over geological time. Eventually, given enough time, the nick point will erode all the way to the river's source, smoothing out the break-in gradient, restoring the river's concave profile. But this takes thousands or millions of years. In the meantime, the nick point exists as a moving feature, a waterfall that's slowly retreating upstream, leaving behind a deeper channel as evidence of where it used to be. The acoustic properties of rivers change with flow rate, making experienced guides able to hear dangerous conditions. Rivers speak in frequencies that reveal their power and mood to those who learn their language. The sound changes with flow rate, with turbulence, with obstacles in the channel. A quiet murmur means gentle flow over smooth rocks. A roar means high volume or steep gradient. Certain pitches indicate certain kinds of rapids, certain patterns of turbulence. Guides who spend enough time on rivers learn to interpret these sounds without thinking about it. They can hear the difference between safe riffles and dangerous hydraulics. They can detect changes in flow by subtle shifts in the acoustic texture. The river is always broadcasting information about itself through sound, and those who listen carefully enough can read that information, can understand what's happening downstream before they can see it. It's a kind of intimacy with place, with process. The river becomes familiar not just visually but acoustically, its voice as recognizable as a friend's. Different rivers have different voices, different acoustic signatures based on their size, gradient, rock type. And the same river has different voices at different flows, different moods expressed in different frequencies and rhythms. Some rivers maintain ice-free sections in winter called polynyas, where warm groundwater keeps channels open. In the depths of winter, when everything else is frozen solid, there are sections of river that remain liquid. Steam rises from the surface in the frigid air. Ice forms along the banks, but the main channel stays open. kept liquid by groundwater that emerges at temperatures above freezing. These are havens of liquid motion in frozen landscapes, defying winter through subterranean heat. Wildlife concentrates here. Birds that need open water, fish that can't survive under ice, mammals that need to drink. The Polynya becomes a refuge, a place where life persists through conditions that would be impossible without this underground warmth. The groundwater might be only a few degrees above freezing, but that's enough. It mixes with surface water and keeps just enough of the channel ice-free. The river continues flowing through winter while everything around it locks down in ice, maintained by invisible sources of warmth bubbling up from below. River deltas are among the most rapidly changing landforms on Earth, growing or shrinking by meters per year. Deltas are battlegrounds where rivers and oceans fight for territory, with the shoreline constantly redrawn. The river brings sediment, trying to build land. The ocean brings waves and currents, trying to erode it away. Whichever force is stronger determines whether the delta grows or shrinks. Some deltas are expanding rapidly. The Atchafalaya Delta in Louisiana grows by several meters per year, building new land into the Gulf of Mexico. Other deltas are shrinking. Dams upstream reduce sediment supply while the ocean continues eroding, and the land subsides and disappears beneath the waves. Stand at the edge of a growing delta and you're standing on brand new land. Earth that didn't exist a few years ago, built from sediment that was once part of mountains hundreds of kilometers upstream. Stand at the edge of a shrinking delta and you're watching land disappear, watching the ocean reclaim what the river built, watching geography actively changing faster than maps can keep up with. The energy dissipated by rivers through friction with their beds and banks is measurable and follows predictable mathematical relationships. Rivers are engines of entropy, converting potential energy into heat that warms the earth by imperceptible amounts. Water at high elevation has gravitational potential energy. As it flows downhill, that energy is converted to kinetic energy, motion. And as the water rubs against the riverbed and banks, that kinetic energy is converted to heat through friction. The amount of heat is tiny at any given point, but integrated across all the rivers on Earth, across all the water constantly flowing downhill, it's measurable. Rivers are warming the planet slightly, imperceptibly, just by flowing. They're entropy generators, turning organized energy, water held at high elevation, into disorganized energy, random thermal motion of molecules. This follows predictable mathematical relationships based on flow rate, gradient, channel roughness. You can calculate how much energy a river dissipates, how much heat it generates. The river doesn't care about these calculations, of course. It just flows, and in flowing, it does work on the landscape and converts energy into heat, following thermodynamic laws it has no awareness of. Some rivers create standing waves where fast water meets obstacles, waves that stay in place while water rushes through them. These are sculptures made of motion, fixed in space but never the same water from moment to moment. Where fast-flowing water hits a rock or submerged obstacle, a wave can form downstream of the obstacle. The wave looks solid, permanent, like it's attached to the obstacle, but it's not solid at all. It's just a shape that water takes as it flows through a particular geometry. The wave stays in place while the water rushes through it, and individual molecules pass through the wave in a fraction of a second. But the wave itself can persist for years, decades, as long as the flow conditions and obstacles remain the same. It's a standing wave, stationary in space but dynamic in substance. Kayakers know these waves intimately. You can surf them, staying in one place on a river by riding the wave as water rushes beneath you. The wave provides the lift, the shape, the force, but it's always different water, always new molecules creating the same pattern. The river demonstrates something profound here, that patterns can persist even when the substance creating them is constantly changing. The Amazon River's tidal bore, called the Pororoca, creates surfable waves that can travel 800 kilometers inland. Twice daily, the ocean sends waves backward up the Amazon, thus turning fresh water into a surfing destination. The tidal bore arrives as a wall of water, sometimes several meters high, traveling upstream at speeds up to 30 kilometers per hour. It's the ocean pushing back against the river, forcing water to flow the wrong direction for a brief time. The wave can be surfed for extraordinary distances. Surfers have ridden the Pororoca for more than 12 kilometers in a single ride, moving upstream on a river wave, carried by tidal energy transmitted hundreds of kilometers from the ocean. It's an unusual kind of surfing. The wave isn't in the ocean, it's in a river, travelling inland, and it lasts far longer than any ocean wave could. The name Pororoca comes from an indigenous word meaning great roar. You can hear it coming before you see it, a sound like continuous thunder travelling upstream. The wave arrives, reshapes the river temporarily, and then passes, leaving turbulent water in its wake. Hours later, the tide recedes and the river returns to its normal flow until the next tide pushes another wave inland. Rivers can maintain hydraulic jumps, where fast shallow water suddenly becomes slow deep water in a visible wave. A hydraulic jump is a visible equation, water solving physics problems in real time as it transitions between energy states. Fast-moving shallow water suddenly slows down and deepens, creating a stationary wave at the transition point. The water goes from supercritical flow, faster than wave speed, to subcritical flow, slower than wave speed, in a turbulent foamy boundary. The jump stays in place as long as the flow conditions remain constant. You can see the exact point where the flow regime changes, which is where the water's behaviour fundamentally shifts. Upstream of the jump, the water is fast and shallow. Downstream, it's slow and deep, and at the jump itself there's turbulence, air entrainment, energy dissipation, the visible cost of changing from one flow regime to another. Engineers use hydraulic jumps intentionally in spillways and channels to dissipate energy, to slow fast water before it can cause erosion. But they also form naturally wherever the right conditions exist, the right combination of flow rate, slope, and downstream conditions. The river creates them without intention, just by flowing through geometry that forces a transition from one energy state to another. The chemical composition of river water varies dramatically based on the rocks it flows over, creating unique signatures, as each river is a liquid fingerprint of its watershed's geology, carrying dissolved mountains in solution. Rivers flowing through limestone are rich in calcium carbonate. Rivers flowing over granite carry silica. Rivers draining volcanic regions might be high in iron or sulfur. The chemistry is a direct record of what rocks the water has been dissolving. You can taste this sometimes. Some rivers taste mineral-rich, slightly bitter or metallic. Others taste clean and neutral. The difference is geology, what rocks the rain has been touching, what minerals it's been dissolving as it seeps through soil and flows over bedrock. The river carries a chemical signature of everywhere it's been. Scientists use these chemical signatures to track where water comes from, to understand mixing at confluences, to identify sources of pollution. The natural baseline varies so much from river to river that you have to know the local geology to interpret the chemistry. What's normal for one river might indicate contamination in another. Each river has its own chemical personality, determined by the rocks it flows across. River terraces, flat areas above the current river level, mark ancient floodplains from when the river flowed higher. These are stairs made by a river cutting downward through time, each step a former riverbed now abandoned. If you walk up the sides of a river valley, you might notice these flat benches at various heights above the current water level. Each terrace is a fossil floodplain, a place where the river used to flow before it cut deeper into the valley. The terraces record the river's history. The lowest terrace is the most recent. The river was flowing at that level just hundreds or thousands of years ago. Higher terraces are older, sometimes millions of years old, marking elevations the river occupied in completely different climatic periods. Each one is a snapshot of the river's former self, preserved as a flat surface in the valley wall. People often build on these terraces. They're flat, elevated above current flood levels, and usually well drained. Towns and farms occupy ancient floodplains that haven't been flooded for thousands of years. We're living on the river's past, on surfaces it carved when it was younger, higher, flowing through a landscape that no longer exists. Some rivers experience ice tsunamis when warming temperatures cause ice jams to release, sending waves of ice blocks downstream. These frozen floods can pile ice higher than houses, reshaping landscapes with solid water instead of liquid. When an ice jam breaks, all the ice that was piled up behind it suddenly releases. It doesn't just flow away, it surges downstream as a chaotic mass of ice chunks, some weighing tons, all moving together like a slow-motion avalanche. The ice tsunami can push up onto the banks, bulldoze in trees, crush in buildings, pile in blocks of ice in random heaps that might take weeks to melt. It's not the water that does the damage, it's the ice itself, becoming a destructive force, solid water acting more like rock than liquid, reshaping everything it touches through sheer mass and momentum. These events are terrifying to witness. The sound alone, ice grinding against ice, cracking and groaning, is like nothing else in nature. And the aftermath is surreal. Landscapes transformed by ice, huge blocks sitting in places they shouldn't be, piled against bridges, pushed up riverbanks, marking the high water line of solid frozen chaos. The biological productivity of rivers is highest where water speeds create optimal mixing of nutrients and oxygen. Life flourishes not in the calmest or fastest water, but in the Goldilocks zone between. Too slow and oxygen levels drop, nutrients settle out, and the water becomes stagnant. Too fast, and organisms can't maintain position, can't anchor themselves, get swept downstream before they can grow. But where the speed is just right, moderate flow with enough turbulence to mix oxygen from the air into the water, enough current to carry nutrients but not so much that nothing can hold on, that's where life explodes. These productive zones support dense communities of algae, invertebrates, fish. The water is alive with activity, with organisms taking advantage of the optimal conditions. Rivers create these zones naturally through their riffle pool sequences, through variations in depth and speed. The most productive ecosystems are found where physical conditions are neither extreme in either direction, but balanced in that narrow range where life can thrive. The river organizes itself in ways that accidentally create perfect habitat, not through intention, but through the physics of flowing water, interacting with channel geometry. Rivers create their own magnetic signatures due to the movement of conducting water through Earth's magnetic field. Flowing water becomes a faint generator, creating electrical currents measurable by sensitive instruments. When conducting water with dissolved salts and minerals, moves through Earth's magnetic field, it generates tiny electrical currents. These currents create their own magnetic fields, detectable signatures that vary with the river's flow rate and direction. The effect is small, but it's real. Scientists can measure these magnetic signatures and use them to estimate river flow without actually measuring the water directly. It's a strange application of electromagnetic theory. Rivers as unintentional electrical generators, producing power too small to use but significant enough to detect. It's another reminder that rivers are more than just water moving downhill. They're conductive fluids interacting with electromagnetic fields, creating measurable effects through basic physics. The river doesn't know it's generating electricity. Doesn't know it's creating magnetic signatures. It's just flowing, and that flow happens to have electromagnetic consequences we can measure and interpret. The oldest evidence of rivers on Earth comes from rocks 3.2 billion years old, showing rivers existed before complex life. Rivers have been shaping our planet longer than anything has been alive to see them. 3.2 billion years ago, Earth had rivers. No fish swimming in them, no plants on their banks, no animals drinking from them. Just water flowing downhill, following gravity, eroding rock, depositing sediment, doing the same work rivers do today. The evidence is in the rocks. Ancient river deposits, cross-bedding patterns that only form in flowing water, rounded pebbles that only happen through river transport. We can read these rocks and reconstruct rivers that flowed billions of years before humans existed, before complex life existed, before anything existed except simple single-celled organisms. Rivers are older than forests, older than fish, older than anything we'd recognize as complex life. They're one of Earth's ancient features, continuously present through most of the planet's history. The rivers we see today are young, but the process of rivers, water flowing downhill, carving channels, building deltas, is nearly as old as Earth itself. Some rivers maintain distinct temperatures in different channels where they braid, creating thermal diversity in the same system. A braided river is many rivers sharing one name, each with its own microclimate and ecology. Where a river splits into multiple channels, each channel can develop its own temperature regime. Shallow channels warm faster in sunlight. Deeper channels stay cooler. Channels fed by cold springs maintain lower temperatures, while channels receiving sun-warmed surface flow are significantly warmer. This thermal diversity creates habitat diversity. Some fish prefer cold water, some prefer warm. In a braided river, both habitats exist side by side, sometimes just meters apart. Organisms can move between channels depending on their thermal preferences, finding the exact temperature they need somewhere within the braided network. The river isn't homogeneous. It's a collection of slightly different environments, all flowing in roughly the same direction, all carrying water to the same destination, but each providing different conditions, different opportunities. The braiding creates complexity, creates diversity, turns a single river into an ecosystem of microhabitats. The settling velocity of sediment in rivers follows Stokes' law, creating predictable patterns of deposition. Rivers are sorting machines, organizing gravel, sand, and clay by size without conscious effort. As water slows, its ability to carry sediment decreases. Larger, heavier particles settle out first. Smaller, lighter particles stay suspended longer, settling out only when the water becomes very slow or still. This creates predictable patterns. Gravel deposits near the source where the river is steep and fast. Only there is the water moving fast enough to transport gravel, and as soon as the gradient decreases, the gravel drops out. Sand deposits in moderate gradient sections. Clay makes it all the way to the delta or ocean, and settling out only in the quietest water. The river organizes sediment according to Stokes's law, a mathematical relationship between particle size, density and settling velocity, without knowing any mathematics. It just flows, and physics sorts the sediment automatically. The result is organized deposits, layered by size, creating the sedimentary structures geologists read to understand ancient rivers that stopped flowing millions of years ago. Rivers on other planets, though dry now, created landscapes on Mars that mirror Earth's river valleys. Ancient Martian rivers carved paths that lasted billions of years after the water vanished. We can see them in satellite images, valley networks that look exactly like Earth's river systems, dendritic patterns spreading across the Martian surface, and channels that carried water billions of years ago when Mars had a thicker atmosphere and liquid water on its surface. The rivers are gone now. Mars is too cold, its atmosphere too thin for liquid water to persist on the surface, but the channels remain, preserved in the dry Martian soil, protected from erosion by the lack of water and wind. They're fossil rivers, ghosts of a wetter past, evidence that Mars once had a hydrological cycle not unlike Earth's. Looking at these ancient Martian rivers, we're seeing what Earth's rivers do, what they've always done: flow downhill, carve valleys, transport sediment, shape landscapes, but on another world, under different conditions, in a climate that no longer exists. The rivers on Mars are memories in stone, echoes of water that flowed when our solar system was young. The Thalweg is the line connecting the deepest points in a river, creating the path of strongest current. It's the river's river, the concentrated essence of flow within the larger channel. If you could trace a line along the deepest part of a river's channel following the path where the water is deepest and fastest, you'd be tracing the Thalweg. It's not a straight line down the middle. It curves back and forth, following the shape of the channel, swinging from one bank to the other in meandering rivers. River navigators know the Thalweg intimately. It's where boats have the most clearance, where the current is strongest. In shallow rivers, the Thalweg might be the only navigable path, the only line deep enough for a boat's keel. Following the Thalweg means understanding the river's hidden geometry, as knowing where the deepest water flows even when you can't see the bottom. The Thalweg shifts over time as the river erodes and deposits sediment. What was the deepest path last year might be shallower this year. The river's internal structure is dynamic, constantly reorganizing itself. The Thalweg is wherever the strongest current has carved the deepest channel, and that location changes as the river evolves. Some rivers maintain year-round flow only because of groundwater contributions called base flow that sustains them between rains. They're fed by invisible aquifers, drinking from underground reserves when the sky provides nothing. During dry seasons, when weeks or months pass without rain, these rivers keep flowing, not from surface runoff, there is none, but from groundwater seeping into the channel, the invisible springs and seeps adding water from below. This base flow is essential. Without it, many rivers would be ephemeral, flowing only during and immediately after rain, but groundwater provides steady, reliable input that maintains flow through dry periods. The aquifer acts as a buffer, a storage system that releases water gradually, smoothing out the peaks and valleys of precipitation. You can sometimes see where groundwater enters. Look for sections where the water is clearer, cooler, where it seems to be bubbling up from the riverbed. These are seeps and springs, points where the water table intersects the river channel and groundwater becomes surface water. The river is sustained by water you can't see, by underground reserves slowly releasing their contents through these invisible connections. River meanders become more pronounced over time through positive feedback. Outer banks erode faster, making curves tighter. Rivers amplify their own curves in a slow-motion spiral that eventually cuts itself off. When a river curves, water on the outside of the bend moves faster than water on the inside. This isn't random, it's a consequence of physics, of conservation of angular momentum, of water having to travel farther on the outside of a curve. That faster water has more erosive power. It undercuts the outer bank, making the curve slightly sharper. The sharper curve forces water to move even faster on the outside, which erodes even more aggressively. The process feeds back on itself, the curve getting tighter and tighter over decades and centuries. Eventually, the meander can become so tight that it almost touches itself. As during a flood, water might cut through the narrow neck of land between the two sides of the curve, creating a shortcut. The river abandons the loop entirely, straightening itself out, and the old meander is left behind as an oxbow lake, a curved body of water marking where the river used to flow before it cut itself off and moved on. The concept of stream order classifies rivers hierarchically, with headwater streams as first order and larger rivers as higher orders. Rivers have family trees, branching and merging according to rules that create predictable network patterns. The smallest streams, those with no tributaries, are first-order streams. When two first-order streams meet, they form a second-order stream. When two second-order streams meet, they form a third-order stream, and so on. The Mississippi River is about 10th order by the time it reaches the Gulf of Mexico, meaning it's the result of countless mergers of smaller streams, a hierarchy of confluences building from first-order headwaters all the way to a massive river. The Amazon is even higher order, the product of an even more extensive drainage network. This classification isn't arbitrary. Rivers of the same order tend to have similar characteristics, similar widths, similar gradients, similar ecological communities. The stream order predicts properties of the river with surprising accuracy. It's a simple numbering system that captures something fundamental about how river networks organize themselves. Some rivers create armor layers of large rocks that protect finer sediments beneath, regulating their own erosion rates. Rivers can accidentally make shields that resist their own erosive power, achieving temporary equilibrium. When a river erodes its bed, it removes fine sediment first: sand, silt, clay. Larger rocks are harder to move, so they stay put. Gradually the riverbed becomes covered with a layer of large rocks with all the fine material washed out from between them. This armor layer protects what's beneath. The water can't access the fine sediment underneath the large rocks, so erosion slows dramatically. The river has created its own protective coating, a layer of rocks too large for the normal flow to move. Erosion becomes very slow, or stops entirely, even though water continues flowing over the armoured bed. The armour layer persists until a really large flood occurs, a flow strong enough to move even the largest rocks. then breaking up the armour and exposing the fine sediment beneath. Then erosion accelerates again until a new armour layer forms. The river cycles between periods of stability and periods of rapid change, regulated by this self-created protective layer. The water in large rivers can take weeks to travel from source to mouth, moving slower than it appears. What looks like urgent flow is actually patient progress, covering mere kilometres per day. Watch a river, and it seems like the water is moving quickly, rushing past you toward the sea. But measure the actual travel time, track a dye release or a drifting object, and you discover the journey is slower than you thought. Large rivers might average just a few kilometres per day in their overall progress from source to mouth. The water swirls in eddies, gets caught in slow backwaters, but moves sideways as much as downstream. The straight line distance might be 1,000 kilometres, but the actual path the water takes is much longer, following every curve and meander. So water that falls as rain in the headwaters might take weeks or even months to reach the ocean, depending on the river's length and character. It's not a quick journey. It's a slow wandering, a gradual progression downstream punctuated by periods of stillness in pools and eddies. The river isn't in a hurry despite appearing to rush. Time moves differently in flowing water. Rivers create point bars, deposits of sediment on the inside of meander bends that mirror the erosion on outer banks. What the river destroys on one side, it rebuilds on the other, constantly redistributing itself. The same process that erodes the outer bank of a meander also creates deposition on the inner bank. Water moving slowly on the inside of the bend lacks the energy to carry sediment, so it drops its load, building up a point bar, a low curved deposit of sand or gravel. Over time, the point bar can grow significantly, creating new land on the inside of bends while the outer bank erodes away. The river isn't moving net sediment out of the system in these sections, it's just moving it from one side of the channel to the other, erosion and deposition in perfect balance, the river maintaining its total width while slowly migrating sideways. You can see these point bars easily. They're the curved sand or gravel beaches on the inside of a river bends, places where the water is shallow and slow. They're the river's construction projects. Land built from material eroded just meters away on the opposite bank. The river is both destroyer and creator, simultaneously in the same curve. The turbulence in rivers creates eddies at all scales, from millimeters to meters, in a fractal-like pattern. Zooming into river turbulence reveals the same chaotic structures at every magnification, endlessly self-similar. Large eddies contain smaller eddies, which contain even smaller ones, all the way down to the molecular scale. It's a cascade of rotational motion, energy transferring from large swirls to smaller ones in a pattern that repeats at every level of detail. This turbulent cascade is part of what makes rivers so effective at mixing. Nutrients, oxygen, pollutants. Everything gets stirred at multiple scales simultaneously. The river is a chaos generator, creating complex flow patterns from simple inputs, water and gravity, just by flowing through irregular channels. The mathematics of turbulence is notoriously difficult. Predicting exactly what turbulent flow will do remains one of the unsolved problems in physics. But rivers solve it empirically, creating turbulent patterns without knowing any mathematics, without needing to predict anything. They just flow, and turbulence emerges naturally from that flow. Some rivers maintain losing reaches where water flows into the riverbed, recharging aquifers instead of moving downstream. These sections reverse the usual relationship, with the river feeding the groundwater that usually feeds it. In gaining reaches, the normal situation, groundwater seeps up into the river, adding water to the flow. But in losing reaches, water seeps down from the river into the aquifer, reducing flow as the river travels downstream. You can sometimes see this visibly. The river gets smaller as it flows, losing volume even though no tributaries are taking water away. The water is disappearing into the ground, infiltrating through the riverbed into porous sediments below. Downstream, the river might start gaining again where the water table rises to meet the channel. These losing reaches are important for groundwater recharge. The river is filling the aquifer, replenishing underground water supplies that might not get much direct recharge from rainfall. It's a seasonal exchange in many rivers, losing during high flows when the river has water to spare, gaining during low flows when the river needs the groundwater's support. The biological concept of river continuum predicts that organic matter is processed differently at each point along a river's length. A river is a digestive system for the landscape, breaking down materials as it carries them to the sea. Leaves that fall into a headwater stream are shredded by insects, broken into smaller pieces, partially decomposed. What remains is carried downstream where different organisms continue the breakdown process. By the time organic material reaches the river's mouth, it's been processed and reprocessed by countless organisms along the way. This creates a gradient of biological activity. Headwater streams depend heavily on organic matter falling in from the surrounding forest. Mid-size rivers depend more on algae and aquatic plants growing within the river. Large rivers process organic matter that's been partially broken down upstream, extracting the last usable energy from material that's already been through multiple rounds of decomposition. The river's a conveyor belt for organic matter, moving it downstream while organisms extract energy at every stage. Nothing is wasted. What one organism can't digest, another organism downstream can. The river's length creates time for complete processing, for total recycling of organic materials through the aquatic food web. Rivers can create incised meanders by cutting downward while maintaining their curving pattern, creating canyon systems. When rivers that once wandered on plains are forced to cut deeper, they carve their wandering path into bedrock. The result is something that seems impossible. Tight meander curves in deep canyons. The curves make sense for a slow river on a flat plain, but they look absurd in a canyon hundreds of meters deep. What happened is this. The river was meandering gently on a low elevation plain when something changed. Sea level dropped, or the land uplifted. Suddenly the river had a steeper gradient, more erosive power. It began cutting downward, but it maintained its meandering pattern as it cut. The curves that formed on a plain got carved deeper and deeper, becoming canyon walls. The result is dramatic. Rivers flowing through impossible-looking curves in solid rock, making tight turns in gorges where there seems to be no reason for the curves. But there was a reason. The curves were inherited from a different landscape, from a time when the river flowed on a surface that no longer exists. The meanders are fossils from the river's former life, preserved in 3 dimensions in the canyon walls. The electrical conductivity of river water reveals dissolved ion concentrations, making it measurable evidence of watershed geology. A simple electrical measurement tells you what rocks the rain has been dissolving hundreds of kilometers upstream. Pure water doesn't conduct electricity well, but water with dissolved minerals does. The more dissolved ions, calcium, magnesium, sodium, chloride, sulfate, the better the water conducts. Different rocks contribute different ions. Limestone watersheds produce water high in calcium and carbonate. Volcanic watersheds might add sodium, potassium, sulfur. Evaporate deposits add salt. By measuring conductivity and analysing which specific ions are present, you can reconstruct the geology of the watershed without ever seeing the rocks themselves. This makes conductivity a useful monitoring tool. Sudden changes might indicate pollution, road salt runoff, industrial discharge, mine drainage. Or they might indicate natural events. Landslides exposing fresh rock, drought concentrating dissolved minerals. The river carries chemical information in solution, broadcasting the composition of its watershed through measurable electrical properties. Some rivers experience hyper-concentrated flows where sediment comprises up to 60% of the mixture by volume. These are rivers that are more rock than water, liquid only in their ability to flow. During certain conditions, glacier outburst floods, volcanic lahars, more extreme erosion events, rivers can become so laden with sediment that they transform into something between water and mud, a slurry thick enough to carry boulders, but still fluid enough to flow like water. At 60% sediment by volume, the mixture is barely recognizable as water. It's heavy, dense, viscous. It doesn't splash, it oozes. It doesn't reflect light, it's opaque, the colour of whatever sediment it's carrying, and it's incredibly destructive, with a density and momentum that can demolish bridges, move massive objects, reshape entire valleys in hours. These hyper-concentrated flows usually don't last long. As the flow spreads out and slows, sediment drops out rapidly. The river transitions back to something more recognizable, though it might take days or weeks for the water to clear completely. But during that brief period of hyperconcentration, the river becomes something else entirely. A liquid landslide, a moving mountain, water transformed into a destructive slurry. River ecosystems can collapse entirely if flow falls below critical thresholds, creating ecological points of no return. There are minimum flows below which a river becomes just a wet place, having lost the essential quality of riveriness. Below these thresholds, the ecosystem can't function. Fish can't migrate. Aquatic insects can't complete their life cycles. The connected pools become isolated, temperatures rise, oxygen drops. What was a river ecosystem becomes a series of disconnected puddles. Sometimes ecosystems can recover if flow returns quickly enough, but if the low flow persists, there can be a point of no return. Key species die out. Invasive species establish. The river corridor dries enough that upland vegetation moves in. When flow eventually returns, the ecosystem that recovers might be completely different from what existed before. This is becoming more common as water withdrawals increase and climate patterns shift. Rivers that flowed year-round historically now experience periods of zero flow. The long-term consequences are hard to predict, but they're clearly significant. A river needs to actually flow to be a river, and there are thresholds below which it can't maintain the ecosystems that depend on continuous flow. The ratio of a river's length to the straight-line distance it covers is called sinuosity, measuring how much it meanders. Some rivers travel 3 times the distance they need to, taking the scenic route to the ocean. And if you measure a river's actual length along every curve and bend, then compare it to the straight-line distance from source to mouth, the ratio is the sinuosity. A perfectly straight river would have a sinuosity of 1.0. Most rivers are higher, 1.5, 2.0, sometimes 3.0 or more. High sinuosity means extensive meandering. The river is wandering, taking long loops across its floodplain, covering far more distance than necessary. Low sinuosity means the river is relatively straight, following a more direct path. Sinuosity can change along a river's length, straight in steep mountain sections, highly meandering in gentle lowland sections. The sinuosity tells you something about the river's history and character. High sinuosity usually means low gradient and erodible banks, conditions that allow meandering to develop, and low sinuosity might mean steep gradient, resistant bedrock, or recent channel straightening by humans. The number captures in a single value how much the river wanders, how much longer its journey is than it needs to be. Rivers create fluvial terraces that preserve former valley floors, building landscapes in layers like geological layer cakes. Walking up these terraces is walking backward through time, visiting the river's former selves. Each flat bench above the current river level represents a period when the river flowed at that elevation, when that terrace was the active floodplain. Then the river cut deeper, abandoning that level, creating a new floodplain below it. These terraces can be stacked multiple levels high on valley walls, each one older than the one below it, creating a staircase of former river levels. The highest terraces might be hundreds of thousands of years old, dating from completely different climatic periods. The lowest are young, perhaps only a few thousand years old. Each terrace preserves not just a former river level, but a former climate, a former landscape. The sediments in the terrace tell stories, what the river was carrying, how fast it was flowing, what the climate was like. Archaeologists find human artifacts in terraces, evidence of where people lived beside rivers thousands of years ago. The terraces are archives, preserving multiple snapshots of the river's evolution through time. The concept of bankful discharge, the flow that just fills the channel, occurs about every 1 to 2 years in most rivers. Rivers seem designed for this particular flow, shaping their channels around this recurring event. As bankful discharge is the flow that completely fills the channel from bank to bank without spilling onto the floodplain. It's not the biggest possible flood. It's a moderate flow that happens relatively frequently, typically once or twice a year on average. This is the flow that does the most geomorphic work over time. Larger floods are more dramatic but rare. Small flows happen often, but don't move much sediment. Bankful flow is the sweet spot, frequent enough to matter, powerful enough to transport sediment and shape the channel. Over decades and centuries, this is the flow that determines channel size and shape. The channel capacity matches this flow almost perfectly in stable rivers, as if the river has sculpted itself to accommodate exactly this amount of water. In reality, the causation runs the other way. The channel is shaped by the flows that occur most frequently at levels high enough to move sediment, but the result is the same. Rivers create channels sized for their characteristic flow. Some rivers maintain persistent fog banks that create unique ecosystems dependent on mist rather than rain. The river becomes atmosphere, generating its own weather that waters plants the rain never reaches. In certain climates, coastal areas, deep valleys, regions with strong temperature inversities, rivers can generate persistent fog that barely moves, hanging over the river and its immediate banks like a permanent cloud. This fog can support plant communities that couldn't survive on rainfall alone. The moisture condenses on leaves, drips to the ground, provides water during dry seasons when no rain falls. Trees grow taller near the river, sustained by fog drip. Mosses and ferns thrive in the constant humidity. The ecosystem is adapted to mist, to moisture harvested from air rather than fallen from sky. The fog zone creates a sharp ecological boundary. Walk away from the river, and within meters the fog thins, the humidity drops, the plant community changes. The river's influence extends through the atmosphere, creating a corridor of moisture that supports life dependent on that narrow ribbon of mist. It's another way rivers create their own environments, shaping not just the land but the air itself. River networks obey scaling laws where the total length of all tributaries at each order follows predictable ratios. Drainage patterns repeat similar proportions at every level, as if following a hidden formula. If you measure all the first-order streams in a watershed, then all the second-order streams, then all the third-order streams, you'll find predictable relationships. There are about 3 or 4 times as many streams of order n as there are streams of order n plus 1. The average length of streams increases predictably with stream order. These relationships hold across different climates, different rock types, different scales. They're so consistent that they're called laws. Horton's laws of drainage composition. The river network organizes itself according to mathematical principles that emerge from the physics of erosion and water flow. It's another example of rivers solving equations unconsciously. The network pattern isn't random, isn't chaotic. It's highly organized, following rules that create predictable statistical properties. You can make surprisingly accurate predictions about a watershed just by knowing a few basic measurements. Predict total stream length, predict drainage density, predict network structure, all from simple scaling relationships. The age of water in rivers can be measured using isotopic traces, revealing how long ago it fell as precipitation. Some river water fell as rain last week. Some has been underground for decades before joining the flow. Water molecules carry isotopic signatures, variations in the ratios of hydrogen and oxygen isotopes that can reveal their history. Young water, recently fallen as rain, has different isotopic ratios than old water that's been cycling through groundwater systems for years. By analysing these isotopes, hydrologists can determine what fraction of river flow is recent precipitation versus old groundwater. While during dry periods, rivers might be flowing almost entirely on old water, groundwater that fell as rain years or decades ago, slowly making its way through aquifers before finally emerging in the river. This mixing of young and old water creates temporal complexity in rivers. You're never looking at water that all fell at the same time. It's a mixture of different ages, different histories, different pathways through the hydrological cycle. Some molecules in the river fell as rain yesterday. Others fell when you were born. Others fell before you existed. All flowing together, mixed in the same current. Rivers create acoustic environments that mask predator sounds, while amplifying prey sounds for animals that evolve alongside them. The noise of flowing water isn't random to river dwellers. It's a soundscape they've learned to exploit. River noise tends to be loudest at frequencies that mask the sounds predators make while moving. But the frequencies where prey insects buzz or splash are less affected. Animals that evolved in river environments have hearing tuned to detect the sounds that matter through the river's constant background noise. Frogs calling near rapids can communicate despite the roar, because their calls are at frequencies the river noise doesn't dominate. Birds hunting insects near rivers can hear their prey even with water rushing nearby. The acoustic environment has shaped sensory systems, creating hearing that's specifically adapted to filter out river noise while detecting biologically relevant sounds. It's a coevolutionary relationship, the river creating an acoustic environment and life adapting to function within it. No, the river isn't trying to help or hinder, it's just making noise through the physics of turbulent flow. But that noise has shaped the evolution of hearing and communication in species that live alongside flowing water. We still don't fully understand why rivers naturally tend toward a state of dynamic equilibrium, where erosion and deposition balance. Rivers seem to seek stability, even while constantly changing, embodying a paradox of motion that finds rest through eternal adjustment. In many rivers, over long time scales, erosion and deposition balance out. The river isn't getting progressively deeper or shallower. It's not systematically removing all its sediment or filling in completely. It's maintaining something like an equilibrium state. We don't fully understand why. There's no external mechanism forcing this balance. And the river isn't consciously trying to achieve equilibrium. Yet through the complex interactions of water flow, sediment transport, channel geometry, and landscape evolution, rivers tend towards states where inputs and outputs balance, where degradation and aggradation average to zero over time. Perhaps it's an emergent property, something that arises naturally from the physics of erosion and deposition. Perhaps rivers that deviate too far from equilibrium create conditions that push them back toward balance, negative feedbacks operating at landscape scales. Or perhaps we're missing something fundamental about how rivers work, some organizing principle we haven't identified yet. The river flows on, adjusting continuously, seeking something like rest through constant motion, embodying a stability that exists only in change. And so we've travelled through 100 facts about rivers, these ancient threads of water that have been carving Earth's surface for billions of years, long before anything was alive to name them. From the massive Amazon releasing more water than the next 7 largest rivers combined, to the tiny Roe River spanning just 61 meters. From rivers that flow backwards with the tides, to rivers that disappear underground and never reach the sea. Rivers are both simple and profound. Water flows downhill. That's all they're doing, really. Just following gravity's pull from high places to low places. And yet in that simple journey, they've shaped continents, created the conditions for civilizations, sustained ecosystems more diverse than rainforests, carved canyons, built deltas, and written Earth's geological history in layers of sediment. Maybe what's most remarkable is how rivers embody change while maintaining identity. The water in a river today is not the water that was there yesterday. Every molecule is temporary, just passing through on a journey from mountains to ocean. And yet the river persists. It has a name, a character, a presence that continues even though its substance is constantly replaced. We're all a bit like rivers, aren't we? Constantly changing, constantly being replaced molecule by molecule, cell by cell, thought by thought. But somehow maintaining continuity, maintaining identity, remaining ourselves even as we flow through time. Rivers teach patience. They teach that small forces, applied persistently over time, can move mountains. They teach that boundaries are fluid. That paths wind and curve rather than running straight. They teach that life flourishes not in extremes but in balance, in the spaces between too fast and too slow, too much and too little. So as you drift off tonight, think of rivers flowing in darkness, doing the same work they've always done, carrying water grain by grain back to the sea, shaping landscapes you'll never see, following gravity's patient pull. They'll still be flowing in the morning. They'll still be flowing long after we're gone. These ancient ribbons of water, endlessly patient, endlessly moving, endlessly becoming what they already are. Sleep well.